Okay, welcome to this module on lean activity analysis. So this is about lean thinking and the whole concept of lean management. It's known as lean manufacturing, lean product development, lean engineering, lean thinking, lean operations. And you'll also hear the concept of the lean aerospace enterprise, the lean hospital. Lean became a term used in the 1990s basically, and it was built on other previous operational management improvement techniques and business process improvement techniques such as Six Sigma, and then it became Six Sigma Lean, but also quality management, quality circles, just in time, and so on. And so we're going to dig into that a little bit here, give you some of the basic concepts behind lean, because in your projects, I want you to be thinking lean. In fact, in your lives, in your future lives, you ought to be thinking lean management and lean thinking just to run your own life in order to eliminate all kinds of waste out of it. So these are reference points. There's many, hundreds of websites on lean management. There's Gemba, which is the Japanese term, Gemba Academy, and also another link here on eliminating waste. Originally, it was all started lean manufacturing, and it was all driven again by the Japanese, by Toyota, specifically Toyota. They became the world-renowned benchmark for lean enterprise and lean manufacturing and so on, and lean engineering, lean product development. They became number one. So it's a systematic process to identify and eliminate non-value-added activities through continuous improvement by flowing the product through flow processes based on a signal from a customer. So it's the just in time. So it's all about flow through. So high speed flowing through and getting rid of waste. That's the essence of lean. The essence of Six Sigma is to reduce variation in the process based on statistical analysis. And when you combine lean with Six Sigma, you get a powerful combination of flow and waste elimination, and also process variation reduction. And all that goes to add up to a lean enterprise. And that is also a component of an innovative enterprise, which we will cover in part 4 of the course. There's been defined, there was originally only 7 sources of waste defined, but an 8th one was added. So we'll go through each of them. So the Lean Institute, Lean Aerospace, and any of these major bodies and institutions around the world have articulated the following 8 specific sources of waste. Overproduction, so making too much stuff you don't need. Wait time, waiting around. So a classic example, you go into a hospital emergency room. If they deem that your emergency isn't real emergency, you might sit there for 6 hours, and then your consultation time with the doctor is 10 minutes. That's a classic case of wait time. And when you're waiting, it's non-value added, but what you do if you're smart, you make it value added. You take your computer with you and you do work. So that wait time, you may be having wait time. This is when you actually turn wait time into value added for you. So wait time for them becomes value added to you. So you work on your computer, you watch a movie, you relax, you use the time to add value to yourself. And that's where smart people use lean thinking to avoid themselves wasting time. Okay, another one is excess inventory, making far too much stuff you actually don't need. Safety stock, too much safety stock. Excess inventory in your home, cans of soup everywhere. Buying 3 cartons of milk and when only need 1 because of the consumption rate in your home. And so you've bought 3 cartons and 2 of them sour. And that's excess inventory. That's not very intelligent, is it? So extra processing, where you're actually overdoing the work, and you'll see some examples of that. So the work might take an action of some action that takes about 10 minutes, but you actually go overboard and do half an hour's worth of work when it doesn't require it. It doesn't require so much effort. And the other waste is transportation. So if you organize your kitchen in your home, where you have the freezer downstairs for your meat, and you have on the third floor your sauces and so on, and you're running all over the house to get all these components to build a dinner. That's an example of wasted transportation time, you moving from place to place. Wasted motions as well. So obviously you would maintain all your components in your work area, so you'd make it ergonomically accessible, so that you're able to reach, and you don't have to reach too far where you're straining yourself. So wasted motions, and we'll get into that, and scrap or rework, where, and again, I'm using personal cooking as an example. If you're frying an egg and you want the egg to be medium, but you keep your temperature's too high, and you overheat the egg and it makes it solid, and you keep wasting eggs, that's scrap, and you're going to have to redo the egg. So you start out with a dozen eggs, you want to make one egg, but you've ruined 2 of them already, so you're down to 9 eggs by the time you get it right. So again, that's a simple example of you're both scrap. You've scrapped 2 eggs, but it's also rework. You have to redo your work. You have to, it should have took you 3 minutes to do it, but now you're into 15, 20 minutes. So these principles, they all came out of high-tech manufacturing, but we can use them in our private lives, and that's why I like to provide personal examples, just so you get your thinking clear about what waste is. It's the same if you're going shopping for transportation at the weekend. If you have your home here and you've got 4 stores to visit, and they're from a circular point of view, opposite ends. So maybe store 1 is here, store 2 is here, store 3, and store 4 is there. If you go like this, so you got your center and you go back and forth like that, that's ridiculous. You probably want to go to store 1, then 2, then 3. You might go back in order to go over to store 4 that's on the other side. But the whole concept is plan your transportation time so that you're using the least route. And similarly, underutilized human resources. This is where you may have 4 people standing around when a job only needs 1 person. So like you've heard the story, 3 people, one holds the chair, the other hands the guy the light bulb, and then the guy actually inserts the light bulb. That's 3 people to insert a light bulb in a ceiling or whatever. So that would be called underutilization. What are those people do standing around? So this is another way of looking at the 8 wastes. And another way to remember them is this concept of downtime. Downtime is waste. If your machine is down, it's not making you money. That's not a good thing. So it reflects defects. O, overproduction. W for waiting. N for non-utilized talent. T for transportation. I for inventory. M for motion, and E for extra processing. So these defects, that's the examples. I give you some examples. Okay. Now, this is just a general industry standard with respect to typically less than 5% is value added. And I've done lots of analysis in various companies, and I've found that usually the value added activity over a particular cycle time of a manufacturing or a product development process, only 5% of the time is, I found maybe 6 to 7% of the time is actually value being added. Often there's over processing, most of it is overproduction, or there's stock, wait and waiting time and transport time. They don't add value to the actual product that you're building and you're making. So waste is anything other than the minimum amount of equipment, materials, parts, and working time essential to add value to a product. That's Ono Teiko, and he's famous for waste reduction. There are 8 key wastes. We went through those, and this is overproduction. So these are all the components coming off the conveyor. This poor fellow here is just completely inundated. This is all his work in progress, and these things are going to come off. Not only is he just has so much inventory sitting around, he's run out of containers to put these in because these are not being picked up and processed for the next process or storage. This is another one of overproduction. Look at all these cars. And this all looks good in terms of the accounting numbers, because all those cars are assets in the company's books. So for example, if each car sells for $30,000 and you've 100 of these, that's $3 million worth of inventory in your books. So you look rich. But of course that doesn't mean to say they're actually going to sell. In addition, as you all know, if cars are not moved fast, they depreciate very, very fast once they go off the line. I mean, 30% of a car, once it's driven out of the factory by the owner, the person that buys it, it's already 30% less in price. Cars do not keep their value. Well, certain exotic cars do, but most mainstream cars don't keep their value. A smart person might want to drive their car for 10, 12, 15 years, but to do that, you would have to put a lot of money into the prevention. Remember we talked about prevention costs, preventive maintenance? So you're going to want to spend a good few $1,000s a year on maintaining the car to avoid yourself paying $20,000 a year on lease costs. And this is the way you would start to think about cars. However, your car, if your image status, and you have a big image issue, then your car, after year 5, when it starts to pay you back, it may not have the required image you want because it's going to be a little bit shabby, scores and so on. And so that's where you've got to decide what your value system is. Do you value a flashy new car, or do you value the economic equation where you're getting payback? Now the car now is really paying you a lot back because your overhead costs are $3,000 or $4,000 a year to maintain it, and it could probably have another 5 or 10 years of good driving left in it. So that principle of thinking is how people and companies think with their machinery and so on, and the assets and the wealth they're building. So let's talk about each of these individually. To produce more than is sold or produced before it's needed, it's a visible storage of material. That's overproduction. Again, that's against lean. You don't do that. You make only what you need. You make only what you're going to sell. You don't make any more. Why would you make the rest? Especially if it's food, it can spoil. Overproduction means making more than is required for the next process. So in terms of the internal processes, makes earlier than is required for the next process, making faster than is required. If you're in a production line and you are faster than the guy here's consuming it, you're building inventory in the aisles, you're just pumping components to the next guy in the process. So you're building all this work in progress inventory, and that's not helpful. So you created a huge bottleneck here, and that's probably to do with his process. And similarly, if you're speeding up and that your feeder process isn't feeding you fast enough, you're waiting around, you're not adding value. So we want to get the whole line to be in balance. So the cause is just in case, right? Not just in time, just in case. Oh no, I better produce it just in case we run out. Misuse of automation. You've got an automated work system, and we may as well utilize the machine. It doesn't cost us anything. Pump out as much stuff as possible. Long process setup. Yep, if it takes the setup time, to set up the process, you want to amortize that. You want to get money back on it. So if it takes you 2 days to set up a particular work center, you may want to pump as many components out of it as possible before you have to tear it down for a new process. On-level scheduling, I just explained that. If he's slower than you and you keep throwing components at him, it'll build up in inventory. You haven't balanced the line flow. And then the scheduling as well. if the master scheduler, one week you're making 1,000 widgets a week, and the next week 100, and the next week another 1,000, and the next 2 weeks 100, you got this up and down. You have a very neurotic workforce and exhausted workforce, because when they're doing 1,000 components a week, they're probably working around the clock, exhausted, and the next week they have nothing to do. That's not level scheduling. You want to be able to level the scheduling out across your work centers and capacity. Unbalanced workload, that's the one where, as I explained about, that process isn't balanced with this process, and this process isn't balanced with the upstream process. And over-engineering the line, redundant inspections. Okay, so here's the next one, number 2. Wait time is a waste, like manufacturing example. So this is the end point from the previous operation, right? So this is the lot, this is a lot like maybe a batch of 10 or 15 components. They're waiting on a tool load, and they're getting ready to be loaded into a pallet and to be transported. So they're sitting around, like I said, those components, they're sitting, and that's called wait time. And this is where you transport them to the stocker, and this is active time, right? So actually some value's been added, Some people may not even think that's value. And then the lot is waiting in the stocker, so it's a wait time. And then there's more active time. You transport it. You're actually still not doing any processing, by the way. You transport it to the lot, and then you've wait time is you're setting the machine up. So the first wafer leaves the carrier. This is I think it's electronic. It's in the electronic circuits, yeah. And this is the next lot processing, active time, and then there's post-processing. The last wafer arrives back in the carrier. But look at all this wait time. Look at the active time. There's wait time, and the operation's completed here. You've wait time here, wait time here, wait time here. That's all waste. And this is another way to look at it. So here's your overall total cycle time. So this is the orders received here, right? And the production starts here, so there's no value added here. This is wait, you're waiting around, your parts are sitting in inventory. And this is when production actually starts. So this is the total cycle time, which includes wait time. But this is the manufacturing cycle, so you've actually started to process. Now, when you look at this manufacturing cycle time, you've got process time when you're actually cutting metal or bending or assembly. Plus inspection time. We know that we don't like inspection. It doesn't add value unless it's built into the product, into the process. Plus the move time, moving from work center to work center, machine to machine. And then queue time. And by the way, this queue time is wait time, because as I move my production to the next work center, that is queuing, which is wait time. That's queuing before he actually consumes it and uses it. So the manufacturing cycle efficiency is the value added, which is only the process time divided by the whole manufacturing cycle. But forget that. Look at the total cycle time. This is this wait time when the order is received before any action takes place, you see. So I can tell you, as far as manufacturing is concerned, when you're cutting metal versus handling the materials and the tooling and setting the machine up, we're talking about 15%. 15% of the time is actually value added. So for every 10 hours or for every 15 hours, only 1 hour of that time, or let's say 100 hours, only 15 hours of that time is where you're actually doing process, where you're actually adding value. That's an awful lot of waste. And that's what they mean by wait time waste. Any time that is non-value added, where the operator must stop producing goods and wait for materials, instructions, the team leader to give opinions, or the equipment downtime, causes unbalanced workload, unplanned maintenance, your machine breaks down, long process setup times. So you want to look at those setup, how you set your machine up. You want to reduce that setup time to as minimum as possible. Misuse of automation, upstream quality problems, on-level scheduling, and then of course poor communications. And that doesn't mean just talking. It means some kind of visible communications that he's ready to receive my components so I can offer him some, he's got a light or some kind of signal. And so you'll see some examples of this as we move forward. I want you to read, you can go look this up on the internet, wait time waste. This is a healthcare example. So this is where outpatient comes in, and these are the visits, and this is the breakdown of the activities from an outpatient that's coming into a hospital for action. So first you have to be scheduled. Then there's the waiting room. You go into the waiting room. So you enter the reception and they enter you in, say you're here. And there's waiting room, and then there's some paperwork to produce. You may have to fill out some forms. Then you see a nurse for 10 minutes or whatever the units are, 10 minutes. You might also have to see a student because they're getting trained. But your real value added here, your real time, where you're speaking to a consultant, i.e. medical doctor, is in this case 10 minutes. So this whole visit time, it took 15 minutes to get you in, where you waited in a line to go to the reception and say, "Hey, I'm Joe Bloggs. I'm here to see the cardiologist." Well, that took 15 minutes. So these are examples from the US. So in this case, it was to see a psychologist. It's a 45-minute hour. So it took 15 minutes to go into the hospital and 60 minutes to wait around before the psychologist actually sees you. Then you have 5 minutes for paperwork. There's no nurse in that case. Student, because they're always training students, so they maybe meet you for 5 minutes. And then you spend 45 minutes with the psychologist. But the total time is 130 minutes, of which 45 minutes was value add. Look at this one, the rheumatologist. Your wait time there is 120 minutes. Your total visit is 170 minutes for 5 minutes with the rheumatologist. This is just incredible waste in the healthcare industry, in the sector. And this one, wait time waste healthcare example, emergency room wait times, proportion of people 18 and over who reported waiting times. So this is from the Montreal Gazette, 2014. Basically, they had an axe to grind, you can tell, with their own government and saying, look, our wait times in Quebec are far, far too high. It's 35% of the total visit is waiting, where in Britain, the UK is 3%. Now, I will tell you that I've been in an emergency in the UK and in Ontario, and this is actually true. The British, there's a lot of complaints over there, but I will tell you that the British emergency and throughput is absolutely amazing. And they actually give you signals and so on. And some of the hospitals I've been in, they actually tell you how long it's going to take before they'll see you. You can see the minutes, etc. They really do lean thinking in these hospitals. I'm afraid to say that it's true in Canada. They don't practice such as of the time of me doing this presentation. But anyway, it gives you a perspective on applying lean and wasted time in the hospitals. I found it to be an interesting case study or examples. Inventories in other ways. You'll be glad to see that we're holding $1.3 million of your standard carpet. Look at all that. Oh yeah, great, but we're not offering that style as standard any longer. So you've invested all this inventory in this carpet and the market tastes have changed. Don't waste too much time on inventory. So it represents the material between the operations due to a large lot production or processes. One of the most frequent types of waste and the most expensive to have is wasted inventory. You're compensating for efficiencies and unexpected problems. Product complexity, that means the tastes change in the marketplace. So as the tastes change, you better be sure that you don't have inventory that belongs to the old taste, the old stuff that was in style and vogue. On-level scheduling, per market forecast, unbalanced workload, unreliable shipments by suppliers, and so on. Reward systems are not good. Okay, 17. So we've seen this whole concept of the iceberg effect. This is another way to look at the sea of inventory. So this is a big container here. This is finished goods coming out. This is raw materials going in. look at all these inventory you have. So the blue represents the inventory. As a C, it's metaphorically speaking. So it's all to do with long setup times, quality problems, line balancing, long transportation, machine downtime, housekeeping, poor scheduling. You know, if your machine's down a lot, and while it's up, make good while it's working. Build all the inventory you can. The problem with that is you're masking these underlying problems. So reducing inventory uncovers opportunities to improve, opportunities that must be addressed. So look at all these issues. Quality problems, supplier issues, housekeeping, poor scheduling. So by reducing your inventory, you're highlighting the needs and the reasons for why you were maintaining so much inventory. Another one is over processing. First, the purchase order will be uploaded and available online to you, but I'm going to fax it to you as well. And just in case you forget, and then I'm going to call you to confirm the schedule date and follow that with a confirmation email. Like, this is over processing. So you're uploading the PO online. You can actually see it. This guy can see it. Why? That sounds kind of crazy. In other words, you're giving me the purchase order online. You're going to email it to me as well. You're also going to phone me about it, and you're maybe going to give it to me physically. I mean, do you not have any confidence in me? But this is over processing. There's like 4 actions there when one will do. So you would design a process where this person and you have agreed, this is the one process we'll use. I don't need to phone you. I don't need to meet you twice. I don't need to have conversations about it. It's all in the process. So avoid mindless conversations, repetitive conversations that don't add value, and look for ways to eliminate waste. Over processing, ice cream, there's 65 flavors. Well, first of all, who needs 65 flavors of ice cream? I mean, that's overly complicated, but this guy's just dropped his ice cream and there's dirt on it, so we've now got 66 flavors. It's a bit silly, but my focus really wasn't on the one that dropped. My focus was on the fact that there was 65 flavors. I mean, think about it. Who actually would assess 65 flavors? Now, what you can do, I've seen stores where you can actually choose all your mixes and ingredients and go, and I mean, you may have 15 mixes, and 15 to the power of 15 gives you endless possibilities for the end result. But that's not storing them. You're not stocking a number of end results. You're allowing the person to choose it from standard inventory and then mix it to give you your unique flavor at the end. But in this case, there's 65, so you'd have a whole work in progress inventory system there that you'd have to go looking through them all, which was over processing. So doing more processing to the parts than the customer really requires, you're overwhelming them. Over processing waste can be minimized by asking why a specific step is needed, why a specific product is produced. All unnecessary process steps should be eliminated. Okay. Causes product changes without process change. Yep. Yeah, see, for example, here in this one, if you want to offer 65 flavors, but you don't want to carry 65 flavors in process, you can give them the ingredients that could result in 65 plus flavors, but you'd have to create the process by which they can go to a mixing machine in the store itself and allow you to mix your own flavored ice cream. We're back to that just in case logic, over processing. Okay. Transportation. We're about to start building on lot 37. So now we need to move the dirt pile over to lot 38. Like, that's double handling. You're actually taking one pile of mud that you need to take to a landfill if you're not going to reuse it for refill here, and then put it into another lot. This is transportation waste. Why would it's double handling and maybe triple handling. Poor layout exacerbates transportation wastes, or is the flow. Transport waste is material movement that is not directly associated with adding value. So if you have all your machines laid out miles apart or great distances apart, you have to transport the material from machine to machine. That's all waste. Why don't you have the machines clustered together in a cell? So the processes should be close together, so material flow directly from process to process without significant delays. Excess transportation may be caused by poor layout, large distances, lengthy or complex material handling, large batch sizes, and so on, multiple storage locations. So the next one is motion waste. So look at this guy with all his wrenches all lying on the floor here, and these are the products that he's assembling. So he's putting nuts on the end of this particular thread. But look at the way he has, in this particular, this is before and after, he has his tools all nicely laid out, nicely organized, not just lying all over the floor. And while he has them nicely laid, look where he has them located. He can just turn around and pick them. He doesn't have to bend and sit around. He's got a workbench. The workbench is big enough to hold, as a little fixture here. Well, he had that. Look at the little tiny table. And he has his tools all, and the nuts here, his tools are behind him. And he has the finished goods are here. So this is in and this is out. So these are complete. So somebody else is going to come and pick them up. But once again, and I hope they pick them up soon, because he's starting to run out of storage space as far as his workflow is concerned, unless he just stacks this on top of this, but he could damage the threads. Anyway, that's how you think, but it's all about reducing motion. And you reduce motion by organizing these in a more sensible way. Wasted motion, any movement that does not add value, looking for tools, walking many steps to get parts into finished goods, more movements than necessary. So the causes: poor people machine effectiveness or layout, inconsistent work methods, failure to take ergonomic issues, the size of people, and so on. Poor facilities or poor workplace organization, housekeeping, extra busy movements while waiting. So this is an example of this. These are components here, and they're all nicely labeled. Look at the labels, different sizes, and they're all labeled. Everything has its own place, and that's a nice storage facility. So scrap or rework is number 7, and here we're looking at weak links in the chain, in the supply chain, where you're only as good as your weakest link, and if there's a weak link in the production process, you're going to produce scrap or rework. And this is an example of scrap, from a production process. Now, of course, it can be recycled, and of course, you do get paid for steel and other kinds of scrap, and you can sell it, but nevertheless, it's still scrap, and there's a lot of high-end value-added labor went into producing it. So you want to eliminate that stuff. So it requires additional resources to correct defects before shipping that are scrapped due to defects. It's just rework. Little or no process control, so that's where Six Sigma comes in. You want to reduce your variation. Poor quality standards, inconsistent quality, where you're actually not measuring quality for the upper control, tolerances, limits and fits, geometric tolerancing in manufacturing, mechanical manufacturing, engineering operations. Lack of or little planned equipment preventive maintenance, because you've got machines that are not running true and are producing scrap because the components of the machine, the tooling, the speed of the machine, the vibrations are not producing fit for purpose products as far as surface finish is concerned, or as far as tolerances are concerned. Inadequate education, training, work instructions, okay, product design, process cannot produce quality. So many processes are failing because in the product design, the products themselves are not being designed for manufacture. So they're putting a lot of the onus on the craftsmen, the tradespeople, to make the judgment as to how a particular component should be manufactured, and often because of poor design for manufacture, this will also result in scrap. The customer needs are not understood. And I underutilized resources, interesting one here. So there's a sink that's overflowing with water. They're all looking at it. I can't believe someone just left the water running like that, this guy says, supervisor. Yeah, I know, it's truly wasteful, and they're still watching it. And someone should do something. Who's responsible for turning the water off? Well, this is a classic, I'm not saying all unions are like this, but this is a classic place where you have union mentality, where each person has a specifically defined job, and none of them are actually responsible for turning the water off. And so they're actually arguing off while the flood is happening. This should be overflowing here. Now look, all unions are not like this, but at one time there was no question in manufacturing. The guy that handled the materials, if he wasn't available, the actual machine operator may not handle the materials and carry them from one work center to another because there was a material handler. And so things didn't get done because he said, that's not my job, that's not in my classification. So the overall company suffers. Now, that mentality, again, has been addressed over the last 10, 15 years, 20 years, mainly because of the Toyota system that you're going to hear about in a minute. The Japanese lean enterprise model has transformed the attitudes in the West. So a lack of involvement and participation of employees in improving operations, so they don't care. They just do their little thing, and if it's not in their area, they don't care about the overall company. Old guard thinking, politics, business culture, that's not my responsibility. Poor hiring practices, you're hiring people that are not looking out for the whole company or looking out for the team. These are all behavioral sciences, by the way. Low or no investment in training, low pay, high turnover. Look, in the Lean Enterprise Institute and the Lean Enterprise Initiative, we call this whole area the people side of Lean. The people side of Lean, not just the technical processes, line balancing, better scheduling, better design for manufacturer, design for assembly, and so on. This is the people side of Lean, very, very important. Management thinking has to drive everything instead of involving those who know best. Okay, and by the way, that last part, the people who actually do the work on the line know more than anybody about that work content. No manager will, even if the manager himself had been 15, 20 years on that job, once that manager moves away from it, he cannot possibly keep up to date with the nuances of a particular work process. The person doing it is the person that's going to have the most knowledge about it. That's just an example, underutilized resources. So there's a guy being wheeled in here in emergency. Why do you need these 4 people to do the wheeling? Now, I'm not saying that they're not adding value when they get to their destination, but they actually don't need 4 people to be walking along with him. And this is an example where one person can most definitely do this job. Maybe, yeah, probably one person, because their steering mechanism could probably do the job. I'm not saying that they're not adding value later on, but in that moment, at that time, it's probably you're not utilizing them. Maybe they could be getting ahead and preparing the operating room for the work to be done. So let's just look at some of the technologies. This is some of the history of Lean. So this whole area is around Lean. And it all goes back to some of the great figures in industrial engineering history. Eli Whitney for interchangeable parts for rifles and so on. Interchangeable parts here in the 1850s. And then Frederick Taylor, you all know about him, the father of scientific management, which was time and motion studies, which aligned with the Henry Ford production line, the flow lines, and manufacturing strategy. So this was worker management issues that he brought in, where workers were broken into their small components of labor and highly specialized. So they no longer, one of the big problems with highly specialization was they no longer were taught to see the big picture. So time and motion and scientific management, while it provided an enormous amount of profits at the time, in later years when more automation was brought in and workers had to understand more than just one component of the production process, that changed the whole, as you will see in the 1980s and so on, that changed the whole approach to scientific management. Now, so again, there are others here. There's Edward Deming, Charles Sorensen, Taguchi Ono. This is the Toyota production system, which happened in the 1980s. But in the 1940s and 50s, there was an emergence of the whole concept of quality management. So it started with statistical quality control, and statistical process control, and total quality. So this was statistical process of the actual manufacturing process. Quality control assessed the output of the process. So the actual products themselves were sampled. So for every 100 widgets, you maybe sample 5 of them and measure them and see what the sampling, how they were performing, and then that would give you an indication if they were starting to go out of tolerances. But then they started to do process control, where started to actually do work in process assessments before the products were produced at the end. And then that led to total quality, where you looked at a more holistic approach, where the employees became part of the process. They weren't just doing measures, they were actually involved in correcting the process themselves. And this was Edward Deming, Ishikawa charts. This is the fishbone diagrams. And there were 2 other Americans, Phil Cosby and Joseph Juran. And I've mentioned before, these guys, especially Dr. Juran and Deming, were embraced by the Japanese and were among the great thinkers behind the Japanese miracle and the rise of Toyota, Toyota's system. And that's Shigeo Shingo and Tashio Ono, who were behind the Toyota production system just in time, and they kicked in the 1980s, 70s and 80s. And then American James Woniak wrote the book The Machine That Changed the World, and coined the term lean manufacturing in the late 1990s. And that was James Womack, and he was sort of accredited with the whole concept of lean manufacturing. But the thinking of lean had started a long time ago. It was always about improving the production process. So here's the thinking and the technology, the lean management technology tools. First you inspected quality into the process, then you had quality control, statistical process control, and statistical quality control. Then you had quality assurance, where you were working on the process itself to assure that the end result was a quality product. So you focused more on the process to create the products. And then total quality started to involve the people and quality circles, teams. So this would have all been from the 1950s, 60s, 70s, 80s. This would have been in the 80s here. And then the 90s kicked in with Lean and Six Sigma simultaneously arose. And then they joined these in the late 90s. And today we have the total Toyota production system as well, which is built around Lean Six Sigma. So each of these built on one another. Now, I was around in the even the mid 90s, when we were delivering presentations and workshops to a major company in the US, it's a pharmaceutical company. And we were taking a business process management approach, which is what this course is about, and what Paul Harmon's book's about, business process change. But there were gurus in that audience. We were facilitating the whole workshop, and we were taking an overarching approach to helping this company transform. And it was a workshop to look at where they should head. And there were Six Sigma experts in the room, and there was Lean experts, and all of them they weren't fighting, but they were definitely had their points of view that Lean is the only way, or Six Sigma is the only way. And we were saying no, business process management that incorporates Lean Six Sigma. But at that time, these two groups and two silos had not come together. It's since happened. But this was around about the late 90s. It wasn't that long ago. And when it comes to over the long decades of production systems. So here's the Toyota system. This is considered the #1 production system in the world that has now found its way into many other circles, and we'll look at those. We'll look at the Lean Aerospace Initiative. So this is Toyota. So goal, highest quality, lowest cost, shortest lead time. Really? Cost, quality, schedule. So you want your cost to be low, you want your lead time, so your schedule, you want to get to the schedule on time, and quality to be always maintained high. And you're building it on these pillars. So just in time, You're just producing what is needed, just the required amount, when it's needed, and where it's needed. So you're not producing any waste. And geotica, detect abnormalities ahead of time, so you're reducing variability. Stop and respond, fix them. Don't allow the line to keep producing waste, that's ridiculous. Harmonize humans and machines, so this is the people side of lean. So this is the whole lean system. Now there's also these Japanese words, Moody, Muri, and Mura. You look them up, but it's all around waste, different kinds of waste. And this is our business process architecture at the very heart. Look, minute output, this is our core business processes. We went through that in previous modules. So it's all built around the processes, well defined. So you're looking to have minimum lead time, and you're basing it on standardized work approaches, Kaizen and continuous improvement, stability of culture and workforce, process stability. And let's just continue here, sorry. So, and you can read this, but basically, Jihoka highlighting visualization of problems. Quality must be built in during the manufacturing process. If the equipment is malfunctioned, the affected machine automatically stop, operators cease production, red light goes up, just in time to function, all parts are made and supplied to predetermined standards. So it means that the machine safely stops, means that should a quality equipment problem arise, the machine detects the problem on its own. So you want sensors in there. As a result, only products satisfying quality standards will be passed onwards. You should never pass faulty products because it's only as you add more value to that, you're adding value to already some errors. It's crazy. You're wasting money because it's going to have to be eventually fixed. And what you're doing is each operator can be in charge of many machines, resulting in higher productivity. And this is the just-in-time productivity improvement. Only make what you need and in the amount needed. Don't overproduce inventory. Don't push stuff down the line when it's not required. Implement a pull system, a Kanban system. When a vehicle order is received, a production instruction must be issued. The assembly line must be stocked with the required number of all needed parts so any type of ordered vehicle can be assembled. The assembly line must replace the parts used by retrieving the same number of parts from parts processing, the preceding process. So it's that flow system. So here's other tools, just in time. So these are examples of them here. So this SMED here is, and you'll see this all documented here, single minute exchange dies. Poka-yoke, is there any mechanism in lean that helps equipment operator to avoid mistakes, which is POKA. TPM, total productive maintenance, just to let you see these. This is Hijunka, produced Hijunka is a Japanese word that means level loading. Takt time, the maximum amount of time in which a product needs to be produced in order to satisfy customer demand. We would also call it the critical path. So the Lean Institute created and adapted many Japanese words. I never personally did this. It became like a cult. And so when we're in Western management, everybody would be going around using Japanese terms instead of Western terms like waste, or downtime, or setup time, or runtime, or rework, or scrap. They used Japanese terms, but part of it was a cult, and is a cult. But also it was people actually embracing a whole language, which required thoughtfulness. So I'm not criticizing it as a bad thing. I just find that it was sort of why it was incredible that it took us to adapt another language in order to change our mindset about production systems. So here's some examples of these tools. Here's a single minute exchange of dies. Now this one isn't about a die, but its principle's the same. So this is where you have a bolt and you have a nut, so you screw that on. Well, all this is waste. That's going to take 40 seconds to screw that on, and you have 100 of these to do, just add it up, that's waste. So it's better that you've no excess thread so that you don't have to wind this around here. But even better, best you've no excess thread, but lead in to avoid cross threading. So obviously when you start your thread, you might get it in the wrong sequence or the wrong alignment. Where if you have this shank here to allow you to place your bolt on top of the thread, it's going to be much faster, foolproof actually. Now look, this one here is an amazing, this is going to be lean at the ultimate. I'm going to give you the link to look this up, but essentially what it is,
But Holland comes in for a pit stop.
in the 1950s, it took about 4.5 minutes to change the tire in a Formula One car in the 50s. So they're changing the wheels.
Holland stays in his seat.
Just have a look.
To get away. Let's watch.
So these guys are doing maintenance. So let's go forward to the 60s. The 1950s, sorry. So let's move forward. So this is 1979.
How long will it take in comparison with the imperturbable young French-Canadian that we're looking at this very moment? And that is a very quick pit stop. Although, yes, outsurging, 20 seconds.
20 seconds in the 1970s, so 1982.
The full distance, and PK is in the pit. Yeah, this is it. Nelson PK now for the first
So here they're assembling the wheels.
We didn't get a stopwatch on it, I'm afraid, because we were looking at Nigel Mansell, but it's a very quick one. There is the fuel going in, and you can see that the mechanics have all got fireproof suits on. The car is up on its own pneumatic jack. Nelson Piquet came into the pit in the lead.
Let's go. So wind it forward. This is 93. So we're 40 years after the 1950s when it was 4.5 minutes. There's the seconds. 4.81 seconds. 2003. So about 5 seconds. 2013, this is where it really gets interesting. So this is the quintessential, this is the optimum performance of lean. Yes. 2.3 seconds. 2014. It's about 2 seconds. 2015. We're at the point now where we're probably reaching the limit. 1.15 seconds. That's it. Let's go to the next. So you know the tasks, each of those, these are all numbered 1, 2, 3, 4, 10, 11, 13, 17, 18. These are their duties, their tasks. So every single one of those mechanics has a task. Number 1 is the rear jack. Number 2 is the rear tire off. Number 3, the tire gunner, gets it off. Number 4, tire on. Number 5, the stabilizer. Number 6, front tire on. Number 7, tire gunner, front tire off, front wing adjuster. Number 14, tire gunner. That's the guys that are, attaching the new tires. Lollipop man. Front, I assume that's the coordinator and tells you when you can go. Front tire on, stabilizer, rear tire off. Anyway, each of them has a role, and they're able to turn that around in 2 seconds from 4 minutes. Here's some of the lean methods. The lights are used to let drivers know when all jacks and wheels guns have been removed so they can leave the pit. So that's their focus, and it's visible. So visualization. And these are some tools. A close look about the custom-made wheel nuts that are used in every Formula One car. They're designed with speed in mind. And the pneumatic wheel guns are specifically tailored to each wheel, and operators are likely to be more agile members of the team. So in other words, each of the guns here for tightening these bolts and so on are custom made for that particular wheel and bolts. Everything's aligned. So the Toyota production system, my company's moving to a just-in-time inventory. You'll deliver when we need it, he's telling him. So your success depends on my company doing what it promises you. And he says we have my deepest sympathy. In other words, when you put the onus on suppliers to deliver when the big companies want, and the tier one companies, the OEMs, I feel a sharp stabbing pain in my chest. In other words, you've got to rely on these people. Let's just quickly look at the Kanban system. Kan is a Japanese word for CAD. Ban is the signal. So it's a signal that you need more parts. You need to be replenished. Card system that produced Toyota originally used Kanban to limit the amount of inventory tied up in work in process. Remember visual pull systems versus a black box push system, which is MRP. MRP pushes inventory out. So you might want to, it's not easy to see this on the film, but basically this is the downstream process. There's a preceding process here. This is the next process. So this guy here, production instruction the production instruction Kanban is removed when an operator retrieves a part. So this operator here retrieves the part and takes the part away with them. Parts are displayed, the parts retrieved to Kanban are transported to the next process. So this guy takes the card, passes it to here, and he goes back with an empty box so that this guy fills that empty box. So you always have one box or two or three, it depends on the quantities and the production flow through. In this particular process, you always have a Kanban box sitting so that when this guy needs it, he's not waiting on him. He automatically can pick it up from here for his, when it's ready to be processed in this particular process, and then he sends a card back and says, fill this box because I have a card, and that card has a certain amount of quantities. So this is the Kanban system. You're never run out, but you're not producing too much either. He only produces when the box is empty. Okay. So various methods of calculating the number of Kanbans, in other words, the number of these boxes. So the number is the average demand during the lead time plus the safety stock divided by the container side, and there's an equation for it. So let's just look at the variables. N is the number of Kanbans, D is the average demand for a product per hour, L is the lead time to replenish it, S is the safety stock of the product, and C is the container size, the number of products in a container. So for example, if we have 150 bottles are produced per hour, which is the average demand, L equals the lead time, 30 minutes equals a half hour. S, which is the safety stock, so it's 150, 7.5 bottles. C is the actual container size, so 25 bottles. So average demand per hour plus the lead time and the safety stock. And here's the equation. So in this particular one where you have 150 bottles per hour, times 0.5 hours is the lead time, plus 7.5 for safety stock, divided by number 25 for 25 bottles, tells you that you need 3.3 Kanbans or containers. So in other words, you need 3 of these containers filled to keep up with the production demand here. Now you could say, why don't you have bigger containers? Well, that would be a material handling issue. Okay. Supermarket Kanban. So it's a very simple one. The customer selects a product, checks it out. The RFID says, oh, that's been replenished from inventory, so that's empty, that spot. Or you're down to a certain amount based on the replenishment requirements. So then the clerk scans it. The computer signals the warehouse, hey, we've only got 3 of these left. We need more, a truck replaces it. So this is a supermarket Kanban, but it's a pull system and it's based on the rules of demand here. In other words, if you know that you're selling 100 of these per week, and that's the typical forecast and the typical trend, you might want to keep at least, you know, if they sell 20 a day, you want to at least keep a couple of days worth of safety stock there. Okay, there's another case study here on trailer utilization lean case study, and that'll be handed out in the class. It's about improving the trailer utilization, and there's the as-is flow in the docks and using pallets and so on. So this is just a summary of the types of waste, examples of the waste, and the recommended actions one takes. It's just a nice spreadsheet. I won't go through it. We've been through most of them. Okay. There's a learning activity. How does lean design relate to business process design? So what's the relationship between lean thinking and business process and workflow and methods thinking? Thank you very much.